Please welcome Martha White. Martha is a professor at University of Alberta, and she works in reinforcement learning and has served in the committee of ICLAIR as a co-program chair and as an area chair in many other machine learning conferences. She also received the IEEE award for AIs Tend to Watch in 2020. Now today, she is going to be talking about advances in off-policy value estimation. So super excited to have you, Martha, and please take it away.
Thank you very much for that nice introduction. So today I get to tell you about one of my favorite topics, which is off-policy value estimation. I've been working on this for a while, so there's actually a long history in this topic, and this talk to me is the culmination of many people's work, and what I would say is actually some answers to what has been a pretty big open question. So it's sometimes rare in research that you really get to see sort of the start of something and then see quite a lot of progress made on it, and that's what this talk is going to be all about, that longer range of progress. But I'm also going to focus it, of course, on some of the work that we have done recently. So it is in that sense, because it's sort of an overview talk of an area and a big open problem, it is educational. So I hope that you'll stop me and ask any questions as I go along, because my hope is that you'll learn something useful about value estimation in RL. Okay, so I know many people here, of course, are going to know about RL, but I'm going to try to get to this topic, but make sure that I start in the beginning and that we're all on the same page. So the problem setting I'm imagining is that the agent is in the regular Markov decision process setting. So the agent environment interaction is formalized as a Markov decision process. I want to emphasize upfront that even though we often say that we're in Markov decision processes, me and many other people, I believe, really mean that can be in the partially observable setting. So we're always going to assume when we formalize these things that we have states, value functions and such are going to be defined on top of states, but those states may not necessarily be observable to the agent. So that when the agent actually does approximation, it may have to use histories or recurrence to actually estimate values appropriately. But all our definitions, including our definitions of objective functions, are going to assume some underlying state. Okay, so if you're in the audience thinking, oh, the Markov setting is not that interesting, I just want to point out that we're often thinking of either the partially observable or the fully observable setting. Okay, so the particular thing that's of interest for me here is the off-policy setting. So the agent environment interaction means that there's an agent that actually follows a behavior policy, but it might want to learn about a different target policy pi. So some examples of this, I would argue that most of RL really is the off-policy setting. Whereas as soon as you're using something like experience replay, you're really in the off-policy learning setting. So the agent updates with experience that's stored in a buffer, and that buffer was generated by a different and older policy B. So already there, you're in the off-policy setting. Other interesting settings that are maybe less often seen is the high confidence policy improvement setting, where an agent is going to follow a policy that it trusts. Let's say it's some default policy to start. It's going to gather data, and then it's going to try to learn a new, better policy, off policy from that data. Once it's confident in that policy, it's going to adopt that as a new policy, then it's going to deploy that. And again, it's going to gather new data and learn off policy there to get an even better policy and so on. Okay, and then another setting where we care about off policy learning is one where we learn many options in parallel. So an option is a little policy for a subtask in the environment, and an agent might want to learn many options in parallel, little like macro actions or solutions to subtasks that it could then chain or use to reason about the larger problem. Okay, so these are the things I have in mind when I'm thinking about off-policy learning. And so the key thing that makes this off-policy is that the agent is following this behavior policy B. And so the state visitation distribution DB is determined by B. So where the agent goes and sees states is going to be determined by our behavior policy. All right, and so our goal now is going to be to do value function estimation from this off-policy data. Okay, so one other thing I'd like to motivate is that value estimation, we often talk about prediction and control in RL, and to me, value estimation is just maybe the central problem in RL. Whether you're doing prediction or control, I believe we're going to need to learn value functions. So that's why I think it's so important to actually be able to estimate value functions. So if we think about many of the different things we do in RL, they often involve estimating values. So maybe we just want to learn what are the values for a policy. This is our prediction setting. So our value function VPi is going to tell us what the expected return is from a state under my policy pi. So here I'm evaluating how much return am I going to get from my policy pi if I were to follow policy pi. Okay, so we'll do that. We care sometimes about estimating VPi. We might want to learn action values QPi. One of the reasons we would want to learn action values is that then we can do policy improvement. So if I learn Q pi, I could do our usual policy improvement result where we take greedy actions and we know we're going to get a better policy. Okay, so that's one way to use value function estimation to then do control. And of course, we can also directly estimate Q star using things like Q learning. And even if we're going to use policy gradient methods like actor critic, we're usually going to estimate values so that we reduce variance when we're learning with policy gradient methods. So value function estimation is very important. Okay, so with that preamble, let me just start telling you a little bit more about what the actual objectives are going to be and what our algorithms are going to look like. So the value estimation problem is, that we can't usually perfectly approximate V pi. We are not in a tabular setting. We're going to have some function space math cal f, and I'm just going to ask a quick question. Can you guys see my mouse when I use my mouse? Maybe not.
Yes.
Yes, wonderful. Okay, so we have some function space f. We're going to try to find some approximate values v, and our goal, if we could, would be to minimize this value error objective. Okay, so what this is saying is we have our true values v pi. We are approximating it with our v here. That's from our more limited function space, and we're trying to minimize these square distances between v pi and v with some weighting d of s. And usually we'll think of this as our state visitation distribution. But anyway, this is we're always going to have some different weights for each of our different states, where that weighting might be, if I see a state very often, I'm going to update there more often, so it implicitly has higher weighting. Or I might just say that some states are more important than others. So this is the generic form where we're allowed to have some weighting on our states. Okay, and so here when I write this objective, I'm going to assume for now that we have finite states. All of these results really extend to the continuous state case, but it's just easier to think of finite states. And then we'll think of V as a vector. So that's why we have this norm on vectors. I have a vector of values for V, I have a vector of values for V pi, and I can compare each of those entries in my vector and get these squared errors. All right, so that's what our objective would be if we could do it, but we can't actually directly optimize this objective, sort of for obvious reasons. We don't have V pi. So implicitly, our goal is, though, always to reduce the value error, and then we're going to have to find algorithms that use some surrogate objectives to do so. Okay, so far to have tried to get to minimize value error, the standard approach has been to use TD methods. So either for prediction, we use temporal difference learning or Q learning in the control case. Okay, and the TD update, just to sort of give as a reminder, looks something like this. We imagine we have our weights, we have a parameterized value function v hat, that gives us our estimate v hat for our current state s, and then we're going to update our parameters w towards the TD error delta times the gradient of our value function at that current state s. Okay, where this gradient is with respect to our parameters w. Okay, and this is our standard TD error, r plus gamma v hat minus in our next state minus v hat in this current state. But this term is giving us an approximation of our return, and this is our estimate of the return. Okay, so that's what we typically use if we just say, let's go try to get an estimate of the value function. And now the issue here is that though this is the very standard approach and continues to really be the go-to strategy, so the method underlying DQN and other DRL methods, that TD is really only sound under on-policy sampling and linear function approximation. And once we leave those two settings, TD has soundness issues. It's not really a sound algorithm anymore. So it's questionable whether we should be using it. So we know that it can diverge either under off-policy sampling, or if we even just move to nonlinear function approximation, which of course we would like to do, it can also diverge as well. So we have this big gaping hole that we would like to say, well, let's actually try to derive sound algorithms, because we are of course going to be moving to both nonlinear function approximation and off-policy sampling. Okay, so as a result, there really has been this flurry of work saying, how can we do this better? And this has largely been around these gradient-based methods. But to do that flurry of work, we sort of need to understand what our underlying objective is so that we can do standard strategies like use gradient-based algorithms, which we know should have soundness properties. Okay, so defining a good objective for this is not obvious. And I'll just tell you what the two main objectives have been, and then how we can actually generalize that into one unified objective that I think is actually the right objective going forward. Okay, so one of the objectives that has been considered is the squared Bellman error. Okay, and so this comes from the fact that we know that the true value function should satisfy the Bellman equation. So we have these true values v pi. We know that v pi satisfies v pi is equal to t times v pi. But this is just saying if I apply the Bellman operator to v pi, then it tells me what is the expected value of the reward plus gamma times value in the next state. And so we need v pi of s to equal to this expectation. And then of course we exactly have that v pi is equal to the expected return. Okay, so this is really just a condition for the true v pi. Then, so instead of just using it as a condition for v pi, we can of course use it as an algorithm as well. And so here we can say, let's go find the best v that we can, where v minus tv is as small as possible. So then we've approximately gotten a v that satisfies the Bellman equation. Now, once we're approximating v, we may no longer be able to get a v pi that exactly equals tv. So that's why we're always going to have some error here. Okay, so this is actually a nice objective. It's reflecting what we would like, a v that is almost satisfying the Bellman equation, but it has not been as popular because of what is called the double sampling problem. So later I'll show you why it's the case that we have a double sampling problem here. But the reason it's a problem is that in order to get an unbiased sample of the gradient of this objective, you actually need to have essentially a simulator. You need to say, from the state that I'm currently in, I need to be able to sample one next reward and next state, and then I need another independent sample of a reward and next state that I could see. And then you can get an unbiased sample of this gradient, and otherwise you can't. So that's a problem. So another direction has been to try to formalize what's the objective underlying TD method, since TD is not optimizing the squared Bellman error. Instead, TD is optimizing this thing called the linear projected Bellman error. Okay, and so here the idea is that instead of trying to find a v that is close to tv, we're going to go find v that satisfies this projected fixed point problem. Here this projection says tv might take me out of my space. I'm going to project back into that space for my function approximator v, and I'm going to find a v that is equal to this projected fixed point problem. And I'll show you a picture of that in a second. In any case, the objective looks a little different. It's called the projected Bellman error for that very reason. Now we're going to try to find v that minimizes the distance to the projection of t times v. And that's actually what TD is doing implicitly. So it wasn't that TD was derived by saying, here's my objective, it's the linear projected Bellman error, and now I'm going to take the derivative. Rather, retroactively, it was realized that TD is actually optimizing this objective indirectly, not with a gradient-based method. Okay, now here the issue with using this objective is that it's restricted to the linear setting. And of course, we want to use nonlinear function approximation. Okay, but so then before I move on to what we're going to actually do to resolve this and think about what our final objective is, I just want to point out how these objectives can look different. So whenever we're visualizing these things and imagining what are these surrogate objectives, what we imagine is that our true v pi, this plane is like the space spanned by our value function approximation. So let's say we're stuck in a linear space spanned by some features. V pi can't be represented by any value function in this space because it's outside of our space. So we're going to draw v pi out here. Our best value function in our space is the one where we project v pi down into our space. So that's the best we could do if we were to minimize value error. So the value error minimization would give us this v best right here. Okay, so we can't, of course, do that. And what we'll get is instead these surrogate objectives would give us some other solutions. So this is, of course, a hypothetical drawing, but this is something that could occur. So the projected Bellman error solution would be one where if we're in our space and we apply our Bellman operator and it brings us out of our space and we project back into our space, the projection would bring us right back to the same point. So this would be a solution we could get under the projected Bellman error. And under the squared Bellman error, the regular Bellman error, this could be what a solution looks like, where we're in the space, we apply the Bellman operator, which takes us out of our space, we can't represent that point. But this is still the smallest error that we could obtain under the Bellman error, that this is a pretty small gap here. So that's the best solution we're going to get. Okay, and then the actual distance to the true values is, this is the solution we found for Bellman error, this is the solution we found for the projected Bellman error. And so, in this example that I'm giving, the projected Bellman error gave us a worse solution than the Bellman error. That may not be the case, but here you can see how there's no reason they should give you the same solution. They're different objectives, they're going to have different properties, and neither of them are doing exactly what we want, which is to give us v best, is the main purpose of this drawing. Okay, so sort of summarize that motivation of what we're trying to do here, and the history is, it was recognized that TD could diverge under off-policy sampling, and actually also under nonlinear function approximation. And so it was actually an open problem for a while, how we could resolve this issue. And particularly the Bellman error does actually let us resolve the issue, but it's hard to use because of this double sampling problem. So there was significant progress made in the early 2000s where with the introduction of the linear projected Bellman error. Once we had a clear objective, then people could say, okay, now I'm going to go use my standard optimization tools to optimize that objective. So there was lots of different gradient temporal difference learning algorithms developed that were trying to minimize this linear projected Bellman error. Okay, so then the remaining issues were that the projected Bellman error was primarily for the linear setting. There was some attempts to generalize it, but they were relatively complex. And the Bellman error was difficult to optimize due to this double sampling problem. But actually then more recently, there's been some nice developments about using a conjugate form. So that's what I'm going to talk about now. Okay, so the key points for this talk are that we're going to use the same conjugate form to develop a generalized projected Bellman error that brings together all these objectives and helps us understand better what our solutions are and helps us derive algorithms. Okay, so the key things that we're going to be able to do by having this generalized objective is that it lets us take advantage of theory that was sort of scattered in, some theory for Bellman error, some theory for linear projected Bellman error, and bring it together into some new theory just about the generalized projected Bellman error. And it's going to let us come up with new algorithmic approaches to optimize a generalized projected Bellman error. Okay, and this is work that we've just recently submitted to JMLR. It's a paper on arXiv called the Generalized Projected Bellman Error for Off-Policy Value Estimation. And we also have some other recent work that I'll mention at the very end of this talk. And this is with my PhD student, Andrew Patterson. Okay, so now let's actually get started. So the outline of this talk is going to be, I'm going to tell you what the projected Bellman error is. Then I'm going to tell you a little bit about the theory that we can get by looking at this generalized projected Bellman error. And then I'll show you some nice results highlighting that by actually going and trying to optimize this generalized projected Bellman error, we can improve on standard approaches that we use now, like DQN. So we have some, I would say actually some surprising results that often when you come up with the new sound thing, you do about the same as what exists, and it's always a little disappointing. But here we're actually consistently finding that using these gradient-based approaches well is just better than using TD, and it's probably what we should be doing going forward. Okay, so maybe this is a chance to pause in case there's any questions before we switch into really diving into what this objective is.
Seems like there are no questions, Martha. You have been crystal clear.
Okay, let's do it. And hopefully, one of my goals here with this slight history lesson is that something as technical as the generalized projected Bellman error is really only interesting if you know why the problem matters. So hopefully at this point, you know why we care about this and why we want to have a good objective for this problem. And if it's not clear, that's also a question you could ask. Why do we care about these particular objectives? Isn't TD just fine? Is a perfectly fine question. But you'll see anyway how we can do better than TD. Okay, so when we move to this generalized projected Bellman error, I'm going to need a little bit of notation. So like I said, we're going to stay in the finite state case. I've already told you that this is our parameterized value function. So we're going to imagine we have some limited function space like linear functions or the space of two neural networks with two hidden layers. I'm going to talk about this as our TD error. So the TD error depends on our current parameters W. So just to be clear, I'll write it as a delta of W. And whenever we talk about the expected TD error for a given policy pi at a given state, that's exactly the Bellman error that we just saw before. So it's applying T to our value function and looking at how different is that from the actual value estimate I have now. And I'll mention also that everything I'm going to say first is going to be for estimating V pi for a fixed policy, but actually all these objectives can be generalized also to the control case, which the paper does. Okay, so the first thing to notice is that the Bellman error can actually be written in this way. So the Bellman error was just the difference between TV minus V. So we can write it this way, which says that I'd like to minimize the expected TD error from a given state, and I want that squared error to be small across all states. And I think this is actually a more interpretable definition of the Bellman error. Please make my TD error as small as possible in all the states. Okay, so this is the first time we'll see why this objective is not that easy to optimize. So, so I just wrote the Bellman error here. If we take the derivative of the Bellman error, this is where we should be straightforward to just nicely optimize this objective, and we should have a sound algorithm because gradient descent, we're just going to assume here has nice soundness properties. And TD is not a gradient descent algorithm. Okay, so if we take the derivative of this, we're just going to use the chain rule. The 2 is going to come out in front. We're going to have this inner term, and then we're going to take the gradient of this term. Okay, and then so here already we can see what the double sampling problem is. We need an estimate of one expected value and an estimate of another expected value that are producting each other. Okay, so if we're in a given state S, I would need one sample to get a TD error here, and then I need a separate independent sample to get an estimate of the gradient of the TD error. Because otherwise, if I use the same next reward and next state, then really what I would be estimating is this. I'd be estimating delta times gradient of delta. And we know the expected value of x times y is not equal to the expected value of x times the expected value of y. Those two things are different. So here, if we just had one sample, we would be using this, which is not the same as what our actual gradient estimate should be. Hopefully that makes sense.
Maybe a quick question, Martha.
Yes.
So the way we have defined the Bellman error, right? So D of S is, the state visitation density, right, over here. So now if I was doing just TD error minimization, right, then typically you would have an experience replay buffer, you would sample state action states, right? So now, in expectation, you would be optimizing something which looks very similar, right?
Okay, right. Very similar to, for example, this thing right here.
Yes, yes.
Okay, good. So I think the question here is, how is this different from what we do in the TD case? Like when we take an experience replay buffer, we grab a triplet and we do a TD update.
Yes, yes.
Okay, good. Let's see if I can answer that. So the D of S, I guess, is not that important. We can't imagine that the D of S is like the frequency of states that we see in a replay buffer. So let's imagine we just have one big batch of data,
Okay.
which just tells us how much we see each of the different states. And then when I grab a triplet like SA, S prime, R, if I were to do a TD update, maybe sometimes it's thought of as that TD is doing a gradient of a squared, like the squared TD error. It's maybe what you're thinking of. So the main difference here is we could compare this to putting a squared on the inside here. So let's imagine we had put the squared on the delta inside this expectation. Then it would be fine. Then actually we would have just, this would in fact be that gradient. It would be the gradient of having put the squared on the inside here. And then we could sample that easily. But so that's one other alternative. You are right. We could minimize what's called the mean squared TD error.
Yeah.
Right. And so the mean squared Bellman error is not doing the same thing. So TD isn't minimizing the mean squared Bellman error, but actually nor is it minimizing the mean squared TD error, because we don't actually take the gradient of this delta. Rather, we leave out one part of it, which is why TD is called a semi-gradient method. Because when we take the gradient of the delta, we either have a target net for the next thing, or anyway, we don't take the gradient of V at S prime. Okay. So actually there's no algorithms that I know of that people use that actually use this full update, which is the gradient of the mean squared TD error. And one of the reasons is, we have obviously tried it since that's such a nice, easy algorithm to use, and it just doesn't work very well. Like it produces pretty bad value estimates. And again, this archive paper explains a little bit why it's not a very good objective to use.
Okay. So I guess the main takeaway is, when people are doing TD error, they have the square inside, right? So they're doing the expectation of TD error square, right? Versus over here, it's like, A plus. So that is what causes issues to come in, which you don't encounter otherwise. Okay.
Right, exactly, for the double sampling problem. And I should mention here, when I'm talking about these objectives, I'm not assuming we have target networks yet. So all of our TD errors here assume that V hat S prime W and this W are the same. Target networks is another direction to try to resolve this issue of the fact that when we take semi-gradient approaches, we've left out the gradient for this term, like these fitted methods. But even there's a question about exactly what objective they're optimizing, since their objective is changing all the time. So here I'm assuming, let's ignore target networks for a moment, and let's go back to our standard TD error that has no target networks, and we're trying to look at what's the objective in that case.
Yeah.
Okay, good. Yeah.
Another quick question.
Yes.
Is one objective where the square is on the outside of the expectation versus where the square is directly on the Bellman error? Like, is there a sense of which one is more correct?
Yeah, good question. Yeah, so if we were to put the square on the inside, that would be called the mean squared TD error. And why would one be more correct than the other? Okay, if you think about what it's doing to put the squared on the inside versus the outside, Okay, so when we do it on the outside, I'm just going to quickly flip back to this. The expectation of the delta here is saying, I want to make sure that the distance between V and TV, like the Bellman operator applied to V, is small. Like you're trying to make that distance small. If you put it on the inside, now you're saying, I want the distance between R plus gamma V in the next state and V to be small. I want these numbers to be small, which means you're going to suffer a little bit from stochasticity. So if your rewards and your values in your next state, like if there's a lot of variability in the rewards and next state, you can see, you'll get a different solution by trying to minimize the squared distances here than you will this squared distance, because this is already taking an expectation over next states and rewards. So this is removing all that stochasticity there and just saying make V equal to the expected reward plus gamma next state. And this minimizing the square root of this would say, make those numbers small, which means you're going to care about the variance as well. So what you can see is that the mean squared TD error, if you put a squared on this delta, is going to look like minimize the mean squared Bellman error plus make sure that the variance of the values for the next state are small. And so to answer that question anyway, we generally like the Bellman error better because our goal is to find a V where the distance here is small. Like we would like to find a V that satisfies this Bellman equation. And we don't necessarily care about this variance term. It's hard to ever say that one objective is better or worse than another. There could be some settings where minimizing that variance is good. In all the experiments we have ever run, the mean squared TD error is not a good objective. So I don't think it's the right choice. Does that answer the question?
Yeah, that was useful. Thank you.
And in some ways, the trade-off is happening, right? I mean, I guess you're getting a more stable target by taking the expectation because you are averaging over the variance. But estimating that is going to become challenging, right? Which I guess what you will, discuss,
Right, exactly. Yeah. So in the end, if we could minimize this thing, that would be easy. But then we're telling V, you need to be good at predicting yourself into the future. Like you need to minimize this Bellman difference, but also make it so that you're easy to predict. Like that's essentially what minimizing the mean squared TD error would say. Make it so that it's not so hard for V at S to predict you at V at S prime, which is not necessarily what we want. But then you're right, to minimize the thing we really want, we're going to have to do something smart algorithmically. But I think that's the right thing to do. The right thing to do is to say, here's the objective I want to solve. And now let's try our hardest to solve it. And then we may have to give up. But in this case, we didn't have to give up. So that worked out. Okay, thanks for those questions, guys. I'm sure other people had them. Okay, so what we're going to do now anyway is say that, it's going to be hard to sample this gradient. So we're going to have to estimate part of it. That's exactly what you were just suggesting. So in order to figure out how we're going to estimate it, actually what we're going to do is rewrite it in a different form. And then it's going to be much more obvious how we're going to estimate it. And what we're going to do is this very usual thing you do in optimization is we're going to introduce an auxiliary variable, and then we're going to have this joint optimization where the auxiliary variable is going to estimate part of our objective and make it easy to do our update. Okay, so this is the main steps for getting this new formulation. It's beautifully simple. Okay, this is just rewriting the Bellman error. So I'm just reminding you here, the Bellman error is these squared expected TD errors. Now we're going to use this biconjugate form for the squared function. So if I take a squaring of y, I can always rewrite it exactly this way. Okay, so we're just going to plug that in. Y here is our expected delta. So that's the first term, 2 times expected delta times h minus h squared. So we're just directly plugging in this biconjugate form, so there's an equals here. And then now we're going to pull this max outside of this sum, where if we say for every single state, if I'm allowed to pick any h of s, then it's the same as having picked a scalar inside this sum. Okay, so we're just swapping this max outside here. This is typically called interchangeability, but for our finite state case, it's just sort of obvious that it's allowed. Okay, and then now we have this new function here. And what has happened is we have a new additional variable h. We're gonna have to learn this auxiliary variable h that's gonna try to approximate these TD errors. But now what's gonna be nice is that computing the gradient of this for a fixed h is very easy in terms of w. Only this part, we only have one part where there's an expectation. We no longer have a double sampling issue. So what that looks like is once we have a given h, we're gonna have two variables now, w and h. But for any given h, if h is fixed, computing the gradient for the weights is very easy. So I'll just write down here what we saw on the last slide. We have, this is what our new objective looks like, where now we minimize over w, maximize over h. So when we're computing the derivative for w for a fixed h, the h here is just constant, and we're just taking the derivative of this part. And the derivative of the TD error is the reward drops off because it's a constant. We'll have a gamma times the value in the next state and the derivative for the values here. So if we look at taking the derivative of delta, reward drops off. We have a derivative here and a derivative here. And then we just have this h of s out beside it. Okay, so that's the idea. Once we do this reformulation, computing the gradient is straightforward. We no longer have a double sampling problem. And now we've just exchanged one problem for another. Now we're going to have to learn these auxiliary variables h, but at least their update is going to be pretty straightforward. So h is just, though it's not obvious from here, what h is actually trying to do when it maximizes is it's trying to estimate the expected TD error. So we're just going to give the TD error as a target to h, and it's a simple regression problem for h, not even a reinforced learning problem. Okay, so what that looks like is we can imagine what our standard update for value functions looks like. It's this. So there's this green part. We imagine an agent inputs a state S. It goes through, let's say, multiple layers of a neural network, and then it outputs its current value estimate. Okay, now, and you usually do, like, say, a TD update where we go back to this green part, update all of its weights to improve its estimate of the values. And now we just have an extra term. So in addition to having this one head for the value function, we're going to have an extra head for this auxiliary variable h. So h hat here just means we're approximating that h of s, which is the expected TD error. And now the update here, I told you, was relatively straightforward because once we have h, our gradient was just this derivative of v hat minus gamma times derivative of v hat in the next state. This should be an st. And h is estimating our expected TD error. All right, and then h is updated by saying regressing towards delta t. So delta is our current TD error. H is trying to get closer to that. So this is just a regular linear regression update for h, given the TD error as a target. Okay, so this red part is the new part, it's this auxiliary variable. So whenever we do an update, the W is gonna be updated using the output given by h. And of course, h is gonna use W because it has to compute the TD error delta. Okay, so it's kind of actually relatively simple to modify our algorithms to do this. We just have to change our weight update and add this extra head. And if we wanted to do this for action values, which we usually will, we'll often want to go use these for control. The updates are actually very similar. And the main difference is now before, again, we still just had the screen part. We had action values, one output for each action. And now the same thing will have one H for each action as well. Okay, so that hopefully grounds out what the algorithm is going to look like. Okay, so the main thing why this is useful, I already said that it's useful because it lets us compute the gradient update for the weights. But the other reason it's useful then now is once we have this algorithm where we've introduced these auxiliary variables, now it's actually just a standard min-max optimization problem. And we can go ahead and leverage all the theory from optimization that says this is going to converge, tells you things about convergence rates, also tells you how to improve the algorithm with different variance reduction strategies. So it's a nice formulation that way. Actually, good.
So Martha, maybe a quick question over here. So it looks like we have the standard update, but it's multiplied with this term h of s, right? And this h of s target is the TD error, right?
That's right.
Now, if the h of and I guess that is what is causing the correction to happening.
That's right. That's right.
Okay.
Yeah, so that this is what's going to make it so that we have an actual gradient based update for our weights rather than what TD is, which is something else.
I see. And when you're computing the h of s, is it doing a sample estimate or is it doing still the expectation estimate?
Right, good question. So h of s here is trying to output expected TD error, and now it's going to output an approximation of expected TD error rather than the true thing. So the TD error, if h of s was parameterized by like s prime, then maybe it would be a stochastic version of delta. But because it's saying this is trying to estimate expected TD error conditioned on s. So if we go back to this formula up here, it is exactly trying to estimate this part of our objective, which sort of makes sense why it is that we have an h of s here times this gradient of this term. Yeah, it's exactly trying to approximate this.
And practically, would we still do it, sample wise, or would we do it like, is there any cleverness in computing the expectations, or would we just do a stochastic version?
Let me see if I understand that. So I guess h of s is always has to output an expected value of the delta, which is but linear regression is always expected target. But whenever we use it, we can use it with like little mini batches if you want. Maybe that's what you're saying. Like what I've shown you is just saying, imagine I gave you one state. Here's what the update looks like for one state. but we could use mini batches because now it is just a regular gradient descent procedure. So from your replay buffer, you could go grab multiple states and do multiple updates.
Okay.
Same. Okay, great. Okay, so the I just point out with that TD error, the Bellman error, how we're approximating part of that. But actually now once we add an approximation, once we approximate H, that equality that I gave you, H was supposed to be from the space of all functions. It's no longer obviously minimizing the Bellman error because we're approximating that term. So the next thing we can say is that algorithm looks reasonable, but what have we actually done? So this is where now we can say we're approximating the generalized projected Bellman error. So the nice thing we can find is that once we change the space H, we constrain it to also be a small space of neural networks or linear functions or something. Then we can rewrite this form where now H here, this is the space of the function approximator for H, some kind of restricted approximation space. You leave out a bunch of the steps. And what you can find eventually is that this corresponds to, again, a projected Bellman error. So we have the Bellman operator applied to V minus V. And then the projection now is going to be on this new space H. So whatever space H you picked for your function approximator H is going to tell you how you project your errors. So for the Bellman error, you can think of H as the space of all functions. So the projection doesn't do anything because you don't have to project your errors into your space. Your TV minus V is always representable by some function in the space of all functions. And the projected Bellman error had H equal to the same as the parameterization for V. And so depending on how we pick the parameterization for H, it's going to project our errors differently, and we're going to be optimizing a different projected Bellman error. So that's the way to intuit it, that the choices we make for H, how we do approximation, is going to project our errors in different ways. So that means we're going to care about some errors more or less. So without going, I'm not going to dwell too much on that. But the neat thing about it is that depending on this choice, we're going to get to see a bunch of different types of objectives that we could choose. And then now we can reason about which of these objectives will be good. And of course, that's going to be an open research question. So I don't know the answer to that yet. So this is going to be our new generalized projected Bellman error. And here, if H, the space for our function approximators for H is the space, same as the space for our value function, let's imagine they're both the same linear space. So they both say have the exact same features. They're both using tile coding or something like that. Then we would actually get back exactly the linear projected Bellman error. If they're both the same space, but let's say they're a nonlinear function space, like a set of neural networks of depth 5 and some number of hidden layers, then we get a natural extension of the linear projected Bellman error, but now to the nonlinear setting. If we set H to be all possible functions, then it's just the Bellman error like we had before. This one's a little bit harder to do. And then otherwise, there's a whole plethora of possible options between. We could think about what H is going to give us a better projected Bellman error than either the Bellman error or the original linear projected Bellman error. So I think this is a nice open question we don't know the answer to yet. Okay, actually, before I move on to that, I want to make sure that I don't. Okay, so I'm going to skip actually this part. We'll come back to it if there's time, but there may not be time. So the paper goes through and tells a little bit about how good now the solution is going to be under this generalized projected Bellman error. Our goal, whenever we have a new objective, is to say, if I were to actually solve this objective, how good would my value estimates be? So whenever we're thinking of bounds for these results, this is typically what the bounds look like. They usually look like, here's the actual error that I incur. So this is like the value error these are the values I estimated from my objective. So these are the best things I could get under my objective. And so they depend on H and how you weighted your states. Okay, and this is the true V pi. And so this is our value error. All right, and so we're never going to be able to do better than the best possible approximation. This would be the V that minimizes the value error. So if you remember that picture I showed you, this is V pi. This projects that V pi into the space of functions you can represent. So it's the closest V in your space that's going to represent V pi. So this would be the best we could hope to do. And so we're always going to have some constant that's greater than 1 that's multiplying that error. And so we'd like to understand how bad is this constant. So that's usually what our results are going to look like. I'd like to upper bound my value error with some constant times the best possible value error I could have. And then this value error is going to depend on what you pick for H and what you pick for these state weightings. Okay, but in the interest of time, then I'm going to skip past that. There's some interesting insights into how we pick those weightings, and I just encourage you to go look at the paper to to tell you more about that. A nice thing is that we can, in fact, get bounds of this form that says that if we solve our objective, we can upper bound the quality of the value error. Okay, so let's now talk, I'll finish off this talk by talking about now how we're going to make this a bit more practical. So I showed you already how we can use the update for this generalized projected Bellman error, but in practice, that basic update doesn't actually work very well. So you may have found people who've said things like gradient-based methods don't work, and they are right, actually, if you just use that basic update. It just doesn't work very well. So there's a few things we have to pay attention to when trying to optimize this objective. So once we have these two variables, an auxiliary variable h, and we have our primary weights w, the way they interact is going to matter. Okay, so the first point here is that there's actually two ways that we could update our weights. And by that, I mean, there's two ways we could actually sample this gradient for a given h. So the one that I showed you is typically called the saddle point update. It's, like I said, the most obvious way you would sample this gradient. But there's actually another way we could try to sample the gradient. It's called the gradient correction update. And it instead only uses h of s on the second term. So it's like imagine we put h of s times this minus h of s times this term. Here we're going to replace, for the first one, h of s is going to be replaced with a sample of delta of w. Okay, and the reason is that for this first term, the TD error sample is independent because we were given a state. Like, this is not random for a given state. In any case, there's reasonable justification for why this update is an okay choice. But this gradient correction update performs much better than the saddle point update. It's a different way to sample the gradient. Okay, and then the other thing is that when we're actually learning this h, what we have found is that regularizing or constraining this h helps a lot. Like, it produces algorithms that work much better. Okay, now let me just tell you why that makes some sense. So one of the simple ways to regularize h is actually just to use what we do in linear regression, which is L2 regularization. So when we do that linear regression update, instead of just doing a standard linear regression update, we're going to add a little small penalty as an L2 regularizer. And already that helps improve our stability. But more generally, recently, this is the paper I mentioned earlier at the beginning of the talk, we have found maybe one of the reasons why this seems to help so much, why simple L2 regularizer helps. Okay, this is a bit of a complicated slide, but I think it's actually pretty neat. So I'm just going to tell you the conclusion, and then I'm going to tell you what the slide says. Well, what we find is that if we choose other objectives rather than squared projected Bellman errors, so instead of using these squared terms, if we replace it with more robust losses like Huber losses or absolute errors, we can actually go through exactly the same formulation. And what we find is that the final objective looks exactly the same. So this was exactly what we found for the squared case. And the only thing that changes is the space for h. So it changes the function approximation space for h. And in fact, it constrains it in some way. So let me tell you what this example is. So if, for example, instead of using squared Bellman errors, we used a Huber loss on our Bellman error. The Huber loss is this thing where it looks a lot like a squared error near zero, and then it turns into an absolute value. So you don't have this thing where it magnifies bigger errors. Okay, so that's why I sometimes thought of it as a robust loss. So if we use that Huber loss instead, then the function approximation space for h just turns into a clipped approximation space that says h can be any function in this space, but it has to output a value between minus tau and tau. So it can't output just any real value. It's now going to have to output constrained values. So essentially what it's doing is it's predicting the expected TD error, but then project it into the space minus tau to tau. Like, it doesn't allow you to actually output values wider than that. Okay, so that's what I was saying is the insight here is that just by constraining our h more, this is what we have done here, it's like we're taking robust losses instead of squared errors. And that seems to make our algorithms more stable. They perform more consistently across runs, and they're more stable within a run. So I'll just show you a couple of results with that, actually. Okay, so first I'm just going to show you a few control results in simpler domains. Then I'll show you another result aggregated across a more interesting domain called Minotaur. Okay, so here we just have some classic environments we often use in RL: Acrobat, Carpal, Cliff Rolled Mountain Car, and Lunar Lander. These are all relatively low dimensional environments. And yeah, that's all just to say about that. So there's three algorithms here I'm listing. The two most important ones to look at anyway are QRC and DQN. QRC stands for Q-learning with gradient corrections. So that's exactly using these gradient-based techniques, using that second update I said is good. And the regularized part just means adding a regularizer to our H, that little L2 regularizer. And then QRC Huber is the same algorithm, but now constraining H even more so that it's trying to implement something like a Huber loss. Okay, so across these environments, DQN gets to use target networks. QRC, Huber and QRC do not use target networks. And the interesting results here are that DQN is generally quite a bit more unstable for some of these problems, and QRC Huber performs as well as DQN and often much better. So if we look at this black line, QRC Huber is generally outperforming DQN except for in this small initial part in cliff world.
And the regularizer here is the L2, as you said before?
Exactly, that's right. Yeah, so QRC with when it says regularized means with an L2 regularizer, and then QRC here with Huber just means Huber. In fact, just for consistency, we call this QRC Huber. In some sense, the corrections are regularized, but actually we didn't put an L2 regularizer plus the Huber. We just did the clipping, like the constraining on that H.
I mean, one other thing I'm curious about is if in DQN, if we use the Huber loss, to optimize the TD error, if that leads to any improvements or not really.
Okay, in DQN, if you use a Huber loss. Okay, good question. Actually, often it's said that DQN is using a Huber loss because they do this clipping. They take the TD error and they clip it before they actually use it in DQN. And we did, in fact, use that here to make sure it got to do something like a Huber loss, since that's the standard strategy for DQN. Yeah, so we did use that and it doesn't help enough. It's definitely a very coarse approximation to use clipping directly on the delta rather than starting with an objective that is a Huber loss and then deriving from there.
Thank you.
This is just an experimental question, but why would DQN go down and then back up on carpol in particular? Is it from the same seed every time, or like I would expect to see more spread in that experiment?
Yeah, this is over many seeds. So if I really would doubt that one seed would pull that down because this is probably like 100 runs. These are small environments, so we would have run lots of runs. So is that some kind of consistent behavior? That I'm not sure of, actually. It is possible. I do know that in carpol, we have found in other experiments that there's often some interference issues in carpol, like just standard using neural networks in both carpol and mountain car actually usually performs the worst, and there seems to be some interference issues there. Now, you would think that we should similarly suffer from interference. So maybe that's actually suggesting that the other experiments we had where we thought interference was the main problem, rather has something to do with the gradient-based updates. So that's a lot of words to say. I'm actually not sure why it's coming down like that.
Yeah, it's interesting.
Okay, so we did also some other experiments on slightly more challenging problems. So one thing is, it's nice to take some classic problems where we sort of know what expected behavior is and see how well do we perform on each of those. We also wanted to see what happens if you were to take this and run it on a suite of problems. So there's this nice experimental suite called Minotaur that takes 5 environments from Atari and simplifies them so that they run faster and you can do more runs and so on. So we took this little environment suite, and now we want to know how well do the methods perform if you have to do well across all 5 of these problems. So we normalize scores across environments, and then we pick one hyperparameter setting across these environments. So each agent gets to do a hyperparameter sweep, but across now these 5 environments, and he gets to pick the best hyperparameter setting. Okay, and again, we did lots of runs, 30 runs per environment for a total of 150 in aggregate. Okay, so these results look like this. Now there's just one learning curve because we're looking at performance across this entire suite. And here are the 2 QRC methods, the 2 gradient-based methods perform very similarly to each other. Maybe the Huber one's doing a little bit better, but I would say they're performing pretty similarly, and they're both outperforming DQN. So I think this is a pretty cool result, actually, because DQN is a pretty successful algorithm. There's been lots of additions to it, like adding the clipping, like adding target networks. There's a good understanding of how to use DQN. So I think it's pretty nice that just actually adding in these gradient corrections seems to help actually get us this notable improvement. I'll also mention that DQN does actually get to tune over more hyperparameters, and one of those hyperparameter settings is not to use target networks at all. So it gets to sweep from choose to use, not use target networks, and then start to sweep how frequently it actually updates its target network. And yet still we see this nice gap. Okay, so the key takeaway for me anyway is that incorporating gradient-based approaches actually seems to improve on our standard algorithms. It's not too onerous to do. Really, we just add this extra head to our networks and slightly change the TD update. In fact, the gradient correction update really is just TD plus an extra term. So it's actually very similar to the original TD update. But mainly we actually get these improvements after some painstaking time trying to figure out why the standard approach doesn't work. So now realizing that the gradient correction form is very important, and also constraining our auxiliary variable is finally how we've found that these gradient methods are helping us out. So overall, the summary of what I've told you today is that we now have a new objective called the Generalized Projected Bellman Error that extends our linear Projected Bellman Error now to the nonlinear setting and also incorporates the original Bellman Error. This extension now, or this unification, lets us take nice theory and algorithms from both that were developed for the linear Projected Bellman Error and the Bellman Error, and again, bring them under one umbrella and extend them a little bit. And also, I think it opens up a lot of different questions about new algorithms and theoretical analysis. Things like what should our space for H be and things like that. All right, thank you very much. And I hope you have more questions.
Well, thanks a lot, Martha. So I guess the floor is now open for people if they have any questions. Anyone?
From your preliminary results, do you get the sense that it's more important to have a large space for H or a large space for the value function?
Right.
Because you have that slide where you're showing the different nestings.
Whoops, let me just go back. So far we have found that, I'm just gonna go back to the slide that says that. So far we have found that H and F being the same is actually reasonably effective. It doesn't seem to help a lot to make H bigger. So I will say that the bigger that you make the space F for your value function, the less the projection matters, because you become closer and closer to actually be able to approximate the true V pi. And then the projected Bellman error just becomes like minimizing the Bellman error. So in that sense, I guess I would say if you could, you should always make your value function approximation space bigger.
Mm-hmm.
But at some point, that's just not possible. Like we have limitations, the world is vast. So at that point, then I think there is some reasonable intuition that we could make our H bigger, because maybe we need our value function to be fast to query, let's say, like it needs to be a reasonably sized neural network. But maybe if an agent is training in the background or even training offline, you could use much, much bigger networks or even non-parametric methods to estimate H, which is only used in training and not in deployment. You only need it to actually compute that gradient update. Once you are done learning, then you're just querying that green part of the network where you output your value estimate. So there is some reason to think that these two could be different, and we should be okay in some settings for H to be very, very big.
That's very cool. Yeah, thanks.
So maybe one more question. So, I mean, we know that, if we do, TD learning, we end up getting this overestimation bias and other things. So I'm wondering if, this correction ends up affecting any of those biases, or do we expect them to still exist?
That's a good point. I wonder, it might have an impact on it. So far for ourselves, when we have used this for control, you can also just incorporate overestimation bias strategies within the TD error. So yeah. I know target networks is one strategy where you're going to have two different networks, and then you're going to use the actions for a different network. The other way sometimes you can combat overemphasis, at least a little bit, is to use soft max operators instead of using the max. And that can, again, immediately be incorporated into the objective and the TD error, and then you would have a gradient version of that. So in some sense, you could do both. Like they're both helping solve different problems, but it's not clear that they're necessarily orthogonal. Like it's possible that the gradient correction is also helping with overestimation to some extent.
I see. Okay.
It is an interesting point. I guess if we look at the update, it kind of seems like it should, because it's doing if you had a large, let's go back to the update. If you had a large, value estimate for the next state, then maybe it's helping you subtract off some of that large magnitude in the next state. That's possible. I have not thought about it.
Yeah, I mean, it seems like in the DQN line of work, as you were saying, that there have been so many tricks over time that have been developed. And then if you see the rainbow paper, right, I mean, they kind of put everything together, and putting all the tricks together, gives you a massive improvement.
Right.
So, remove some of those tricks, because there are just so many hyperparameters today, and, make more principled elements in it, that would be awesome.
Right, I agree. In fact, I think that's why we're sort of, we've drawn this tree for ourselves one time. Actually, that PhD student I mentioned made this beautiful tree that showed you all the tricks that layered on top of each other. And in some sense, one of the earliest tricks was the addition of a target network. So now if we remove that early part of the tree, it's not clear how the rest of the things impact. It's almost like we have to design our new tree where we say, okay, what happens if we hadn't used target networks? Now, what are all the tricks that we could layer on top to get good performance?
Yeah, it seems like, at least in some of our experience, if you remove the first layer, everything else falls down.
Yeah, exactly. Yeah, they're definitely not independent tricks, that's for sure. Yeah, there's a root to this tree.
Yeah, it's like, you optimize for hyperparameters given that setup, and then it just,
Yeah, and you optimize for tricks given that setup, which is like a hyperparameter, I guess.
Yeah. So I'm also curious, are you scaling this up to like more like Atari games?
Yeah, so one of our next steps is to actually start trying to scale it up. So again, that PhD student, Andy, is looking into doing that next. Yeah, that's more resource intensive. So it's always harder to move to that when there's more algorithm development to be done. So I preface this with, I think we will probably be looking at scaling experiments.
Okay, cool.